Okay, here we have the last question, and it's about magnetism. So the left-hand rule can be used to identify the force acting on a current carrying wire. And people very often get this mistaken. So that's our first finger. First finger starts from F, so it's the field. That is our second finger. Has a C in it, so it is current. That is our thumb. So it's motion, which is also equal to force. So that's why I like to remember it. First is your field, second is your current, thumb is your motion caused by the force. So they want to draw an arrow on figure 2, direction A and B. Now these questions, when you're trying to do it, are quite awkward. So if you turn your entire exam paper, so north is at you and south is away, then it's a lot easier. Let me just quickly zoom out. Okay, so now we just have to point forward and then put our second finger in line with that current. So our thumb is now going into the page. That is acting down. So if we rotate our paper, we just have to point forward and then rotate our middle finger so it's in direction with the current. And then our thumb, just make sure we go into the page in this case. So just two changes that can increase the force. Now hopefully you all remember the equation, F equals Bill, where B is the magnetic field strength, I is the current, and L is the length. If we want to increase the force, we need to increase these two here. So we could increase the strength of the magnet. Or increase current. So just two changes that we can reverse it. Okay, so we could reverse magnets, or reverse current. Because Fleming's left-hand rule, if we reverse either one of those, then we're going to end up reversing the force. So a student made an electric motor to lift a mass, as shown here. And we have a results table. Test result for D is anomalous. That means it is wrong. Calculate the efficiency. So efficiency is useful output over input. So we've got 120 divided by 80, which is 1.5, which is 150%. Which is obviously wrong because you can't have an efficiency greater than 100%. So here, that would be our comment. Efficiency is greater than 100%, which is obviously wrong. It's just a reason. Okay, so if you look here at the timings, 2.4, 1.2, 0.8 and 0.2. So when you doubled the power, it went from 2.4 to 1.2 times. When you double the 40 to get to 80, it's gone down by a factor of 6, not half. So the time must be too short. It shouldn't have happened in 0.2 seconds, so there must have been a mistake there in the experiment.